Now, if you have 4 domains, 3 of them are bonds, and 1 is a lone pair. What you get there is trigonal pyramidal. Not to be confused with trigonal bipyramidal, which you get with 5 domains. So this, you basically can just take the top bond here and turn that into a lone pair. So you've got Y, one going away, and one coming out at you, and a lone pair on top. And the way you can remember this is pyramidal. You can think of the 3 bonds as forming like a triangular base to a pyramid, and they all come up to the point of the pyramid, which is that lone pair. And the last one for 4 domains is if 2 of them are bonds and 2 of them are lone pairs. So this is going to also be bent, actually. So there's multiple versions of a bent structure. Remember, actually, top right here. If this one is bent, so basically 2 bonds and 1 lone pair is bent. 2 bonds and 2 lone pairs is also bent. So what that would look like would be something like this. And for what it's worth, that's actually the structure that water uses. So again, it still would have a tetrahedral electron domain geometry, but it now has a bent molecular geometry. Okay. Next up, if we have 5 electron domains, and they're all bonds, once again, we just go back to what the electron domain geometry is called, trigonal bipyramidal. I'm just going to go with bipyramid because I kind of ran out of room there. Now what this looks like is it's similar to tetrahedral, but like basically if you put another one going straight down, another bond going straight down, I should specify. So we got so that's trigonal bipyramidal. Now here, this is when we start to get to the point when not every bond angle is the same. So the bond angles between so these 3 here, those are referred to as equatorial positions, and the top and bottom one are referred to as axial positions. So between any of the 2 equatorial positions, you have 120-degree bond angles. Between the 2 axial positions, you have 180 degrees. And between an axial and an equatorial, 90 degrees. All right. So next, let me bring out another piece of paper now. I'll keep this going here. So our next one would be 5 domains with 4 bonds and 1 lone pair. So what that is going to be called is seesaw. Sometimes you'll hear it referred to as sawhorse, but most of the time it's seesaw, and yes, that actually is the technical name for the molecular geometry. So basically, marker. You can take one of the equatorial positions and make it a lone pair. And the reason it's called seesaw is you can kind of think it's like the 2 axial positions are on a seesaw, with the other ones being the fulcrum, and if you turn it sideways, kind of looks a little bit like a seesaw, right? Oh, I'm sorry, I didn't actually write that in. So seesaw. So next is going to be 5 domains, 3 bonds, 2 lone pairs. And so what we actually get there is something that's called T-shape. So in this case, we're just going to take another bond from an equatorial position and turn it into a lone pair. About here. Y. And it doesn't matter which equatorial positions you choose. So the fact that I swapped here, it doesn't matter because all the equatorial positions are equivalent. So I just did this way to try to make it a little easier to see. So now I've got 2 lone pairs, and you can see the kind of T shape right there. So that's where the name comes from. And then the last one for 5 electron domains is if we have 2 bonds and 3 lone pairs. So now all of the equatorial positions are going to be lone pairs. And this is actually just going to be another version of linear. Again, now you've just got 3 lone pairs, all in the equatorial positions. And lastly, let's go to 6 domains. So if we have 6 domains, and they're all bonds, once again, we just take the electron domain geometry name, so it's octahedral. And this looks very similar to trigonal bipyramidal. The only difference is that instead of 3 atoms in the equatorial positions, you now have 4. So you get central atom, 1 up, 1 down, and now you've got basically 4 corners covered here in the equatorial positions. So for the bond angles, once again, just between equatorial and axial, you have a 90-degree bond angle. Once again, between the 2 axial positions, you have 180 degrees. The only difference here now is that between 2 equatorial positions, you also have a 90-degree bond angle. Okay. Now, our first derivation from that for 6 domains. I'm gonna be close on room on the paper here, but okay. So if we have 5 bonds and 1 lone pair, so basically you can just take one of the axial positions and turn it into a lone pair. And that's called square pyramidal. Sorry, I kind of ran out of room there. But yeah, square pyramidal. So, because again, just like I said before with the trigonal pyramidal, it was like you had a triangular base that went up to a pyramid. Well, now you've got kind of a square base with the equatorial positions that can be brought up to a pyramid as well. And I'm going to bring out one last sheet of paper to keep going here. So now if we have 6 domains, and 4 of them are bonds, 2 are lone pairs. So now both axial positions are going to be lone pairs. So we got one up above and one below. and that's called square planar. This word planar comes from the fact that all of the bonding domains are in the same flat plane. So now we have 6 domains, 3 bonds, and 3 lone pairs. Now it actually changes up a little bit. So in this case, you now keep the axial bonds, and 1 of the equatorial bonds, while you turn the other 3 equatorial positions into lone pairs. And that's going to be called T-shape, because you can see, just like the one with 5 domains, kind of get a T right there. It's T-shape. And lastly, if we have 6 domains, 2 of them are bonds, and 4 of them are lone pairs. This is going to be very similar to the last one we did for 5 domains. So every equatorial position is a lone pair. You just have 1 above, or 1 bond above, 1 bond below, and this is another version of linear. And those are your molecular geometries.